Alrighty, lads and ladies, welcome back to MAC1140 Pre-Calculus. Today we are going to continue talking about logarithms and exponential functions. Kind of specifically today, we're going to get some practice using those log laws that I showed you at the end of class last time. And then we're going to use all of those properties and definitions together to solve some previously unsolvable equations and things like that. So, forgive me, my new puppy here is kind of velcroed to my chair, and I don't want to hurt him by scooching. Watch out, Bud. Yes, he's very, very cute. Yeah, move over here a little bit. There you go. All right. Another thing, quick reminder, today is the day of the makeup exam. So if you missed exam 2 for whatever reason, right now I think I have 2 people signed up for the makeup. If you missed it and need to take the makeup and have not coordinated that with me, you need to do it ASAP. The makeup is right after class today. It's in office hours, so it's going to start at 3. 95 minutes, like normal. All right. Here we go. This is MAC1140. It's a pre-calc lecture. So where are you going, puppy? And today is the 28th of July, 2021. Today, we're going to practice with the laws from last time. I believe this is like section 4.5 or something. 4.4. No, it's okay, buddy. And then we're going to talk about solving exponential and log equations, which is section 4.6. And I do believe that will be the end of our discussion of logarithms. So just to kind of help everybody keep pace with where we are, where we're going. Right. So we are finishing this 4.6. We may talk a little bit about 4.6. This is not super exciting modeling problems. We can throw that in today probably. But then we're going to start talking about systems and matrices. That is material that is incredibly deep. I'll tell you, the thing that develops as you start to study systems of equations is a field of mathematics called linear algebra. Specifically, when we talk about the algebra of matrices, this is going to be a section that's a little bit tough, and I know we're getting closer to the end of the course, so it's going to be a little bit challenging because we'll be moving quickly. These two sections here, specifically 10.1, I'm sure you've all seen before, systems of equations in 2 variables. We'll move very quickly through that. Spend a little bit of time on systems of equations in 3 and more variables because there's not really anything new there. It's just sort of a generalization of the method. But then my goal is to get you really, really comfortable in the algebra of matrices. So probably 10.1, 10.2, we'll get through those tomorrow. And then 10.3, 10.4 will be early next week. And then we'll finish up the class by talking about sequences and series. Like I said, if there's material that has to be cut, it's going to be the section on conics. And it looks like that may be the case. I may put together some extra videos or give you some worksheets or something for these, but there's a chance that we won't get to those, and that's okay. That's not the end of the world. This material is actually not something that you're going to bounce into in calculus at all. Of course, you'll see these curves, but you won't be seeing them in the way that they're discussed in our textbook, which is as purely geometric objects. You'll be seeing them as graphs of functions. So that's that. We need to talk about log laws. So let's do it. Recall from last time, each of the exponential rules or exponent rules from your previous algebra classes has a corresponding rule relating to logarithms. The base A log of a product of 2 things is the same as the sum of the logs of those things. So the way I say this in my head is that multiplication inside the log is the same as addition outside the log. There's a similar rule for division. Division inside the log is subtraction outside the log. And then there's a rule for powers. So even if the thing inside here, the base inside, doesn't match the base of the logarithm, this power can still come down. And any of these rules, you can use them forwards or backwards. So if you've got a single log with a bunch of shit inside, you would use this going left to right to split it up into multiple logs with simpler shit inside. On the other hand, if you want to combine a bunch of logs that all have the same base into a single expression, you would use these rules going from right to left. So that's the basic vibe. Remember, I give you some warnings, ways that these can often be misused, misunderstood. You need to be exceptionally careful. So without further ado, let's do some practice. First, practice expanding and combining. So we'll do some expansion first. I'm going to say expand as much as possible. Remember, expand means to like widen, to sort of take apart. I'll give you a few here. We're going to have the base 2 logarithm of 6x. We'll look at the base 5 logarithm of x cubed times y to the 6. And the natural log of AB over the cube root of C. All right, so I want to use my rules up there to try and expand these as much as possible. So in other words, every instance I can apply one of these rules going from left to right, I want to do that here. All right, let's number the rules. We call these 1, 2, and 3. Who can tell me which of the rules, 1, 2, or 3, is going to be useful to get started in part A here?
The first one?
Yeah, yeah, exactly. Rule 1, right? Because I have a product inside my log, 6 times x. That's a product. So I've got multiplication inside. That means I can turn it into addition outside. So according to rule 1, this is the same as the base 2 log of the first thing, 6, plus the base 2 log of the second thing, which is x. And this is good. This is expanded. In theory, I could go a little bit further. Does anybody have an idea how I could further expand the log base 2 of 6?
2 to the x equals 6.
Well, I don't have any equations here. I want to, and I'm suggesting maybe we use the same rule, but you agree that 6 is 2 times 3, right? So if
Yeah.
I wanted to, I could write this piece as the log base 2 of 2 plus the log base 2 of 3. And then the plus log base 2 of x is still there. And if we're really feeling fancy, and I need more space, aren't I? If we're really feeling fancy, it's over here so I don't get enough space for the next guy. What is the base 2 logarithm of 2? What is this first term? Think back. Yes, I'm sorry, I heard it. Who remembers the verbal question we ask ourselves to evaluate things like this?
What power?
So what power of the base
1.
gives me the inside? Yeah, the base 2
1.
log of 2 is 1. So this expression could be written as 1 plus the base 2 log of 3 plus the base 2 log of x. And that's as far as I can imagine taking this. Can't take it any further. I think WebAssign would probably accept the first line here, as would I on a test. Probably I would just use a prime here, so it wasn't an issue on a test. Yeah, very good. All right, let's look at B. Again, inside we have a product. I do also have powers, but only the x is being raised to the 3, and only the y is being raised to the 6. So I can't jump in with this rule. Before I could use this rule, I have to have something that looks exactly like this. Just a log with a single thing raised to a power inside. And right now I don't have that. But what I do have inside there is a product like the last one. So I can begin by writing this as the base 5 log of x cubed plus the base 5 log, the base of y to the 6. Divider in here. So this multiplication inside turns into this addition outside. And now each of these looks a lot like this rule 3. I've got the base 5 log of x raised to the 3rd power. So according to rule 3, that's 3 times the base 5 log of x. And similarly, the second guy is 6 times the base 5 log of y. And that's as far as we could go there.
Could you factor out a 3?
Oh, you could. You could.
Okay,
There's a common factor of 3 here. Yep. And if you wanted to, if there's some reason that was advantageous, that would be a legal thing to do. And then we'd have 3 times parentheses log 5x plus 2 log 5y. All right, this bottom one looks a little different. It's an ln. And then also inside, I've got a whole bunch of symbols going on. So first, ln, what does that mean? What is that?
Natural log.
Good, it's the natural log. So do these rules work? These all say log sub a. Like, is this thing one of these things?
Yes.
Yes, it is. All right, very good. Benjamin, why is this one of these? What is A for part C here? Is the base.
A would be E.
Very good. I don't want to confuse that with this A. I probably shouldn't have said that. But yeah, the base here, this is the same as the log sub E of this stuff. So of course these rules work. It's just a special notation. Now, what I like to do and what I recommend that you do when you're trying to expand, pull apart logarithms, inside, ask yourself kind of what's the outermost operation? The truth is that, you know, multiplication, division, kind of in the same tier on your order of operations. But when you look at this inside, I see a fraction. I see a big fraction that's got a bunch of shit upstairs and downstairs. So my advice would be to begin with a rule like this. Don't try to do too much at once. The most common mistake I see here is people doing too much at once. And you'll mess up a sign or you'll mess up a constant. So according to my second rule, rule 2, a log of a fraction is the log of the top minus the log of the bottom. And it's all ln's because the problem starts with L. The base doesn't change when we do this. And now each of these two pieces will require different rules. One thing I advise you to be careful of, this minus sign goes with everything over here. So if I was going to expand this guy into like 2 or more terms, all of them would get that minus sign. Another way to think of it is if a term is downstairs inside the logarithm in the condensed form, its associated term in the expanded form will be negative. It's a good way to check it and remember if you distributed negatives appropriately. Now in this first guy, I've got the natural log of a times b. So that's rule 1 again. This is going to be the natural log of a plus the natural log of b. Multiplication inside, addition outside. This other guy, I'm not going to apply any log rules at this step. I'm just going to rewrite the inside as c to the 1/3 power. Remember, if cube root is 1/3 power, just like a square root is a 1/2 power. So inside here, the cube root of c is c to the 1/3 power. Now I can use my rule 4 on this piece. The first 2 terms don't change. Ln of a plus the ln of b. And then we have minus, that power comes down. So outside the logarithm down front, 1/3 ln of c. I promise you this stuff will be on the test. Absolutely. Going to have you expand some logs, going to have you contract some logs. Something you need to practice with. And again, the trick, if you find yourself getting some of these wrong or getting frustrated, is one thing at a time. Don't try to jump in and do everything at once. Don't try to go straight from this expression to this expression. Go through the intermediate steps. That's how mathematicians solve hard problems, by breaking them down into easier problems. None of us do it all at once. Is there anything we'd like to look at more carefully in these?
So let's say the product AB was in the denominator. Would you need to, and when you split those products up into the sums, log sums stuff, would you need to put parentheses
Yes,
around it? Okay.
exactly. And I think it's worth, let's actually look at an example. So let's expand, do one more. How about e to the x times 2 over the square root of y times z. One more. First, the kind of outermost thing I see here is this division again. So I'll start with my division rule. That's going to be the ln of the top minus the ln of the bottom and then each of these has some multiplication inside. So the first one I would write as the ln of e to the x plus the ln of 2. And then the idea is, yeah, we would need negative and then open a big paren or big bracket, because the negative here is associated with both of these terms. So it'll need to be distributed to each of the terms when you pull it apart. So it'd be ln of the square root of y plus the ln of z, but all of that inside our bracket or parentheses. And then in the next step, I can start trying to clean some things up. The ln of e to the x is what?
X ln e.
That's true. It's x times the natural log of e. We can write it like that. The ln of 2, there's nothing to be done there. It's just the ln of 2.
Oh, wait, is ln to the e also 1?
The natural log of e is indeed 1. So we'll do
Okay,
that
alright.
in the next step. That's fine. Now this negative here is going to get distributed. And that's the thing that we were asking about. We want to be careful. So I'll have ln of the square root of y, and I'll go ahead and write the square root of y as y to the 1/2. And then this will be minus the ln of z. And I'll tell you that on tests, the thing people miss this is the part folks miss. Right? They say, oh, okay, well, this is a product inside, so it's going to be ln root y plus ln z. And they forget that this negative out here really needs to be distributed. Really, when you're expanding that, you're doing it in parentheses. Because both of those terms, again, the kind of quick reminder is that both of those terms were downstairs inside. So both of their terms in the expanded form should be negative. And then it's correct that the ln of e is 1, so this is x plus the natural log of 2, these first two terms, because x times ln e is x times 1, then minus the ln of y to the 1/2. Well, y to the 1/2, that's a power, so that power can come down. So this will be minus 1/2 times the ln of y. And the ln of z, he doesn't have the 1/2 because the z wasn't raised to a power, but he does have the minus because he was downstairs. So that would be your complete or final answer. All right. So I'm glad that you asked. Let's try running some of this back the other way. Oh, one more thing before we do that. I'll say a fun way to generate good problems like these that test multiple skills simultaneously is to, inside the logarithm, put a polynomial that you need to factor. And then once you factor it, you'll have the multiplication inside and you can expand. So that's a wink and a nudge to something that might show up on a test. So just like you can use those rules to expand, you can use those rules to combine. I could take this and say combine this into a single logarithm and expect you to get to here just by using all those rules in the reverse order. I'm going to give you new stuff so we have more stuff to practice. So like 3 log x plus 1/2 log x plus 1. Could be fun. I'll get more space here. B. Let's try 3 times the ln of 8 plus 1/2 times the ln of t minus 4 times the ln of t squared plus 1. Okay. Let's start with these. And the first guy, you have to imagine just running the process we did in reverse. So if I want to put 2 logs together into a single log, they can't have any numbers out front. It has to look like the rule. It has to be log of something plus log of something else, or log of something minus log of something else. It has to just be logs on the outside, no numbers here. So the first thing I got to do is bring these guys up inside. So this 3, come inside, this 1/2, come inside. And again, I advise you to be careful, parentheses, order of operations, all that stuff. So that first term is going to be the log of x cubed. The second guy is going to be the log of, and I would stack your parentheses here, parentheses, parentheses, x plus 1 to the 1/2. And it's the whole quantity x plus 1 being raised to the 1/2, not the individual terms. I hope that's clear. So from here, I think it's clear we could pull the 1/2 power down and get this. But if this was x to the 1/2 plus 1 to the 1/2, that's not the same as x plus 1 all to the 1/2. in the same way that x squared plus 1 squared is not the same as x plus 1 parentheses squared. So these parens inside here, they're important. Now that I have these, I've got just log of something plus log of something else. I can use my rule 1 to put those together into a single log. And the inside of that single log would be x cubed times parentheses x plus 1 to the 1/2. And if you want to write the 1/2 power as a square root, go right. Questions on any of these steps?
Would you require us to do the square root of the 1/2 or?
No, this would be fine. Either one is perfectly acceptable. Any other questions on this first combination problem? Okay. The second one is going to begin the same way. If I'm going to glue some logs together into one log, they can't have anything out front. They got to just be ln's or logs or whatever. So first, I'll write this guy as the ln of 8 cubed plus the ln of t to the 1/2 minus ln of parentheses t squared plus 1 to the 4. Again, that stacking of parens is important. 8 cubed off the top of my head, I don't know what that is.
512.
Oh, thank you. Yeah, I guess that's a power of 2, right? We should know that. It's 2 to the 9, 512. Yeah, thank you. We got a computer scientist. Who was that?
I had just Googled it.
Oh, okay. No harm. So this first guy is the ln of 212. What I'm going to do is just glue these two together first. So 8 cubed is 212. Let me write 2, sorry, 512. From computer science, people usually know their powers of 2 really well. So this is going to be the ln of this inside times this inside, which is 512 times t to the 1/2. And then I've got minus the ln of t squared plus 1 to the 4. And while you could multiply all this out, there's no reason to. I wouldn't do that. And finally, now I've got ln of one thing minus ln of another thing. I can write that as 1 ln with the stuff inside. Now 512 times t to the 1/2 is 512 times the square root of t. And then downstairs I've got t squared plus 1 to the 4th power like this. And I want to make a note here. This is not ln of 512 root t over ln of t squared plus 1 to the 4. There's a big, big difference between this and this. They're not even close to the same. I know it kind of looks similar, and you get used to this idea of division, subtraction, and it's tempting to write things like this sometimes. But this shit is very, very different from this shit. Not only are they not algebraically equivalent, you plug in numbers, you're not going to get the same thing. They just mean totally, totally different things. This is like x over 2 all squared. This is like x squared over 2 squared. Same sort of error, only far more severe in the case of logarithms. This is one of those common mistakes, right? Okay, anything we'd like to look at more carefully in any of these last few examples? All right, then before we can start talking about equation solving, there's one last thing I need to show you. It does kind of relate to that little note or common error. It's called the change of base formula. Suppose someone gives you a natural log, but you really want a base 2 log, or someone gives you a base 5 log, but your calculator only has an ln button. How do you compute that? Well, for any A's and B's, which are positive, we have the following. The base A logarithm of x is equivalent to the base B logarithm of x divided by the base B logarithm of A. So I think of this like somebody gives me a base I don't like. I don't like the base A. I want to use base B instead. That's just the base B log of the old thing divided by the base B log of the old base. Two special cases. If you look at your calculators, they probably have LOG buttons and they have LN buttons. So if you're given some other base logarithm of some shit, and you want to put that into your calculator, that's the same as the ln of that shit divided by the ln of that old base. Or if you want to use the log, the base 10 log, that's the log of that shit divided by the log of that old base. So this first guy, I'm using E for B. And in the second guy, I'm using 10 for B. So let's clear E. That's all. So you can convert any one logarithm base into another base log. Mostly useful for calculator stuff. Okay. I don't think we need to beat these to death any more than we already have. So what I do want to talk about is solving equations. This is the start of section 4.5 now. Recall that all exponential functions are one-to-one. On the one hand, that means we can define the inverse, and that's where logarithms come from. But what this really means, by definition, this means that the only way two outputs from an exponential can be equal is if those inputs were equal. And in fact, this goes both ways. The left direction is obvious. If x is equal to y, then a to the x is equal to a to the y. But the right direction is not obvious, that if a to the x and a to the y are equal to each other, then x and y are equal to each other. This is sort of the fundamental thing that allows us to define logarithms. It can also be useful for solving some really simple equations. For example, I could use this to solve 5 to the x equals 125, or 3 to the x equals 1 over 27. I'll do one more after this, but let's start with these. So what I want to do is make use of this fact. I realize the x's and y's kind of over here, x is on the left, y is on the right, over here, y is on the right. It doesn't matter, right? Equality is the way we do this is if the base is the same on both sides, then you can set the powers equal. That's what this says. If you've got an equation and both are like 5 to something, then you can just set the somethings equal to each other and solve from there. So the way we get started here is by rewriting the right-hand side as a power of 5. 5 to the x is 5 to the x. 125 is 5 to the 3. And now, by the orange box property above, x has to be equal to 3. Nothing crazy going on here. The fun is when you want to try to rewrite that right-hand side as a power of the base on the left, sometimes it can be a little bit tricky. So here I'll go through a few steps. 3 to the x equals 1 over 27. Well, I know that 27 is 3 cubed. So this is 1 over 3 cubed. All right, so the 3 to the x just stays 3 to the x. 1 over stays 1 over. But downstairs, 27, I know I'm trying to rewrite that as a power of 3 because the base over here is 3. So 27, I go, oh yeah, that's 3 to the 3. Now on the right-hand side, I rewrite 1 over 3 cubed as 3 to the negative 3. Rules for exponents. And then finally, by the orange box statement, this is equivalent to saying x is equal to negative 3. Okay. These can get a little bit more challenging, but it's very limited what you can do with this, because after you've isolated the exponential term over here, you need the thing on the other side to be an integer or nice power of that same base, which is not always going to happen for you. Let me see if I can find another clean example like this. Anything else obvious? Yeah. So we're starting always kind of easy. So here's one more example of this property in use. Suppose I have 10 raised to the power of 2x squared minus 3 is equal to 1/10 raised to the power of x squared minus 9. The left-hand side is a power of 10. The right-hand side is a power of 1/10. So if I can write both the left and right-hand side as a power of 10, I'm on my way. So first things first. Note that 1/10 is 10 to the negative 1. So that right-hand side is really the same as 10 raised to the negative 1 times x squared minus 9. Another rule for exponents we've used here several times. The rule, remember, is a to the b all to the c is the same as a to the b times c. So 10 to the negative 1 all to the x squared minus 9 is the same as 10 to the negative 1 times x squared minus 9. I just remember to think of x squared minus 9 as a single quantity, so it gets parentheses. All right. Now, both sides are powers of 10, 10 to something, 10 to something. So by the 1-to-1 property, I know that 2 times x squared minus 3 is equal to negative 1 times x squared minus 9. So that's 2x squared minus 3 equals negative x squared plus 9. And now this is a quadratic equation. You can always solve these. I'll add x squared to both sides, subtract 9 from both sides, and we'll get 3x squared. And negative 3 minus 9 is minus 12 is equal to 0. Factor of 3, and you get x squared minus 4 equal to 0. And then you can factor this further. It's 3 times x minus 2 times x plus 2 is equal to 0. So once you get to your quadratic equation in the third purple step here, this guy, you know you're good to go. We can always solve these. Worst case scenario, quadratic formula. Here we're lucky, we pull everything to one side and factor, and it factors nicely. So the solutions to this equation are coming from the roots of this polynomial. Those are positive 2 from this guy and negative 2 from this guy. 3 is never 0. Those are the solutions. Those numbers solve the equation. All right, like I said, these can get a little bit more exotic, but you're not going to see anything terrible. The fun stuff happens when these get impossible. So let me first ask, is there any one step here we'd like to look at more carefully?
Yes, please.
Mm-hmm. Which step?
Oh, no, I just need an extra time.
Oh, sure, sure. All right, while you do that, I'm going to refill my coffee. Buddy. All right. This looks a lot simpler than the last one, but it's actually much harder.
Because the bases are not the same.
Yeah, exactly. Erica nailed it. There's no nice way to write 3 as a power of 2. No obvious way. Now, I know a solution exists. It's really the intermediate value theorem that does it, but we can look at the graph of 2 to the x, remember what that looks like. This is 0, 1. Here's 1, 2. Here's 2, 4. And the line y equals 3. So sorry, in black here, this is the graph. Y equals 2 to the x. And then in blue, here is the line y equals 3. Right, it's a constant function. Its graph is a horizontal line. So I can see a solution, 2 to the x equals 3, where these two curves touch. Right here. Here's my solution. But what the hell is it? Well, I can be reasonably confident that it's bigger than 1 and smaller than 2, right? Because it's clearly between 1 and 2. But I don't know what it is. The trick to solving equations like these, so the challenge is precisely what Erica said. They're not the same base. So the business we were doing up here, where you've got 10 to something else, you set the powers equal, no nice way to do that. So the trick is to use logarithms. Specifically, we're going to take logs on both sides. Remember what the third property of logarithms is. If you have a log of a power, the power can come down. Taking square roots here won't get rid of the x. It would just change the exponent to x over 2. Taking the xth root on both sides won't even take care of things, because then you'd have 2 equals 3 to the 1 over x. And that doesn't really make things any better. But if I take both sides of 2 to the x equals 3, and I shove them inside any logarithm, your choice, your choice. I'll use the natural logarithm. So you take both sides and you put them inside of a logarithm. One, this is kosher because the natural log is the inverse of a one-to-one function and is therefore itself one-to-one. Two, this will do the job because now this power can come down. So this would then become x times the ln of 2 equals the ln of 3, which means x is equal to the ln of 3 over the ln of 2. That's it. That's what this number is. It's the natural log of 3 divided by the natural log of 2. And remember, that's not the same as the ln of 3/2. Right? Very, very different, log over log versus log of the ratio. Not the same. So this is it. This is it. You're done. You cannot simplify further. You could write it as a different base using that change of base formula. This is, in fact, the base 2 logarithm of 3. And you could use the definition of the base 2 log here also if you wanted to get the job done. So here I took the natural log of both sides. I could also take the base 2 log of both sides. Shit, this thing just turns off whenever it wants. Sorry, it's going to take a few seconds for it to come back. Remember how we defined the logarithm. It's the inverse, base A logarithm is the inverse of the base A exponential. So the thing on the left is a base 2 exponential. In some sense, then, the most natural choice would be the base 2 logarithm. But in practice, everybody uses the natural logarithm. So I could take the base 2 log of both sides. And this has the advantage of simplifying a little bit faster. What is the base 2 log of 2 to the x? What is this?
Just x.
It's just x. Yeah, to what power must I raise this base 2 to get this inside 2 to the x? That's just x. Or you can think of it like the power coming down, like we did in the previous one, and then the base 2 log of 2 is 1. So this just gives you right away x as the base 2 logarithm of 3. And by the change of base formula, the base 2 logarithm of 3 is the same as the ln of 3 over the ln of 2. Just two different ways of writing the same thing. This is good. We get our solution. This is bad because I don't really know how big that is. And this is one of the very few places where you'll hear me say calculators are all right. If I ask you for the exact solution, the exact solution is just either one of these, ln3 over ln2. Those are the exact solution. We're out of RAM. Why is shitty little emulator sucks down so much RAM? .5849. We'll call it 1.585. Okay. The exact solutions are this divided this way or this way. This is an approximation. The truth is, this number is irrational. It's not a nice number. It's transcendental. It's not the root of any polynomial. It's a really gnarly irrational number. I have to launch a separate instance for each one. So on a calculator, I'd ask for the ln of 3, divide by the ln of 2, and there it is. All right, still approximate. And you can check that if you raise 2 to that power, approximately 1.585, you get something very close to 3. But if you want the exact power to which you raise 2 in order to get 3, these are the only ways to write it, unless you've got, infinitely many decimal places you're willing to carry around. The big tool here, take logs. It's one of 2 new verbs, 2 new operations, just like square both sides or divide both sides by 7. You can take the logarithm of both sides. Totally new operation. And it's a big, big deal. The partner operation to this is exponentiate, which would mean to put in the exponent of. But we're going to get a little more practice with this before we do that. Here's my solution. All right, solution is base 2 log of 3, or approximately 1.585. And we see, even just from our graph, our crude hand-drawn graph, a little bit, between 1 and 2, close to the middle, tiny little bit closer to 2 than it is to 1. Pretty fucking good just from that crude hand-drawn graph. This is how we solve exponential equations. Let's try another one. I want to solve this guy. Before you can take logs, you need to get it in the form of the previous equation where you've got something to your variable stuff is equal to something else. So here, this -1 is messing things up. So before I introduce any logarithms, I need to isolate the exponential. If I add 1 to both sides here, I get 10 to the x equals 25. And 25 is not a nice clean power of 10. So I will need logarithms here. There's no way to write this as like 10 cubed or anything like that. So now I take logs. What are the steps? Let's say isolate the exponential. Then take logs. And again, we could use whatever base logarithm we wanted, but really everybody uses the natural log. So the ln of 10 to the x is equal to the ln of 25. Now on the left-hand side, the ln of 10 to the x is x times the ln of 10. And the right-hand side is still just the ln of 25. Don't be intimidated by the notation. ln of 10 is just a number. You need to respect the notation, but don't be intimidated by it. This is a constant. We want to get x alone. This constant is multiplying x. So to get x alone, I just divide both sides by this. You can't divide both sides by ln. You can divide both sides by the ln of 10. ln is a function. The ln of 10 is a number. And you're done. And if you want, you can approximate it. I don't have an emulator for the TI-30, so I apologize for the 84 here. This appears to be about 1.398. And we can check if we want that if you raise 10 to the power of 1.398, you get something very, very close to 25. Again, approximate. This is an approximation. On your tests, I'll be asking for exact solutions almost all the time. If you give me an approximate solution instead of an exact solution, I can't give you credit. So it's really, really important that you know how to get to this, not just some calculated procedure. Let's try one that's slightly harder. Just one here that I liked, yeah. E raised to the 1 minus 4x. Let's say 3 of these are equal to 6. First step, isolate the exponential. The 3 is not a part of the exponential. This is the exponential term. So what do I need to do? I need to divide both sides by 3. And that gives me e raised to the 1 minus 4x equals 6 divided by 3, which is 2. Then the miracle step where we take logs. And I'll always use the ln e to the 1 minus 4x will now be equal to the ln of 2. On the left-hand side now, I can use that property of logarithms, the same one we've been using, to write this as 1 minus 4x times the ln of e. And over here, I just have the ln of 2. Now, in this particular problem, there's something really nice. And that's the value of this piece. What is the natural log of e?
1.
Very good, it's 1. The base a log of a is always 1. Or what power of e do I need to use to get e? 1. So this is really just 1 minus 4x is equal to the ln of 2. And now you can solve for x. This is a linear equation now. Subtract 1. Divide by -4. And you're golden. That's job done. Okay. These can get more complicated, but the steps are always the same. The steps to solve an exponential equation. First, isolate the exponential. This is the term that has variables in the exponent. 2, take logarithms. And remember to always take the log of both sides. 3, use properties of logs. To get the variable down and out of the log. And then 4, solve the resulting equation. Sometimes that resulting equation is going to be super simple, like the ones we've seen. In theory, it could be a quadratic, or it could be some other polynomial. It could be a rational equation. You know, after you get the variable stuff down out of the power, if this was 1 minus 4x squared, then at this stage, we would have 1 minus 4x squared equals ln2. That'd be a quadratic we'd have to solve. It'd be a little bit harder. But the big deal is it's no longer an exponential equation. Step 2 here, where you take the logs, always undoes the exponentialness. I'd like to show you some more complicated examples. Okay. Before I do that, I want to make sure that you are 100% comfy with these. So is there anything at all here that feels funny, or if like this was the test, you'd be like, oh. Okay, harder example. Let's see. Jump next. Yeah, I gotta scoot. You're gonna kill my back. I know, baby. I know. Again, lots of ways these can be more complicated. I don't want to spend all the time in the world, but let's do this one. 2 to the 3x plus 1 is equal to 3 to the x minus 2. Here, both sides are exponentials. But on both sides, the exponential terms are isolated. There's no like +7 hanging out over here, or this isn't being multiplied by 6 or something, right? So we're going to begin by taking logs. And as always, you'll see me use the natural log. Base 2 or base 3 logs could work here also, but you know, there's different bases on either side, so I just say, fuck it, use the natural log. And now you can apply those properties of logarithms on both sides. On the left-hand side, you'll have parentheses 3x plus 1 times the ln of 2. And on the right-hand side, you'll have parentheses x minus 2 times the ln of 3. The parentheses out front are important. If you omit those, a bunch of things can go wrong. Just remember, when you're bringing something down out of the power, it comes down as a chunk. It's a single term. Now I want to isolate the x's. That's my goal. So I'm going to blow everything apart. I'm going to distribute everything. This is 3x times the natural log of 2 plus 1 times the natural log of 2. I'm taking this ln of 2 and I'm distributing it. And I'll do the same thing on the right-hand side. That's x times the ln of 3 minus 2 times the ln of 3. Okay. Again, don't be intimidated by the notation. Just remember this is a number. This is a number. It's one number. So this term has an x in it, and this term has an x in it. The others do not. So the terms with x's, I'll pull to the left, and the terms without x's, I'll pull to the right. That gives me 3x ln of 2 minus x ln of 3, subtracting the x ln 3 over, equals negative 2 ln 3 minus ln 2. And from the expression on the left-hand side, because I've taken all the x stuff over there and gotten rid of all the non-x stuff, I can factor in x. Having done that, this is x times some number. So to get x alone, I will divide by that number. Negative 2 ln 3 minus ln 2, all divided by 3 ln 2 minus ln 3. And there's some cute symmetry here, which hints that maybe if we were very patient, bringing this inside as a power and then combining, bringing this inside as a power and then combining, we might be able to make it look a little better, but who cares? This is it. You're done. I have one more equation kind of type that I want to show you. It's a different feel from this though, so I'll give you a second to digest. Any questions on this one? Okay, last example of an exponential equation. Let's look at, let's see. Yeah. E to the 4x plus 4e to the 2x minus 21 equals 0. The trick to solving such a thing is to recognize, observe, that e to the 4x is really e to the 2x squared. Same rule, right? That's that a to the b all to the c is a to the b times c. 4x is 2x times 2. So that's e to the 2x times 2, which is e to the 2x squared. So I can rewrite my original equation as e to the 2x squared plus 4 e to the 2x minus 21 equals 0. This is secretly a quadratic. The way most people would solve this is by saying something like, I'm going to let u be e to the 2x, which would mean u squared is e to the 4x, because e to the 2x squared is e to the 4x. Or even, we already wrote it like this, so you don't even need to think about it like that. But yeah, that's what's going on here. So this would be u squared plus 4u minus 21 equals 0. We're making a little substitution. Now I can factor this, and in theory, I could do this with any polynomial problem. Take any homework problem from the set before the test, where you had to factor big polynomials, and do this sort of thing with it. I could replace that polynomial with like an exponential polynomial. Once you get to that substitution step, now you'd have to factor, and maybe rational roots theorem is required, maybe synthetic division is required. But here, this is fairly easy. This is u plus 7 times u minus 3 equals 0. So we get the two solutions in terms of the variable u. U equals -7 and u equals 3. Now to finish things, remember we were given an equation asked to solve for x. Telling them what u is doesn't get us anywhere, because my reader wouldn't even know what u is unless I told them I made this substitution. So you have to go back. This means e to the 2x is -7 and e to the 2x equals 3. I guess I should be saying or here, right? These are the solutions. To solve each of these equations, I would take the natural log of both sides. Oh, you can't see that negative in there, can you? Yeah, it's -7. Let me rewrite this line because this is a sticking point. So here we'd have ln of e to the 2x equals the ln of, make that real clear, that's a -7. The other guy, this is going to be 2x times the ln of e, or just 2x, equals the natural log of 3, because you know the ln of e is 1. So you get x equals ln of 3 over 2, or 1/2 ln of 3. What about the first one? Does anybody have anything to say about this expression here?
It doesn't exist because of the negative.
Excellent. The natural log of -7 is not a real number. Remember, the domain of the natural log is just 0 to infinity, the open interval, 0 to infinity. You cannot take the natural log of -7. This is not a thing. So there's no solution that comes from this side. That equation really only has one solution, and it's x equals the natural log of 3 over 2. If you want to explore the concept of a natural log of a negative number, take Calc 2 and differential equations with me. I'll show you. It can be done in terms of complex numbers. That's the truth. But does not exist for us is the true statement. Just like you used to say that certain polynomials have no solutions, right? Like x squared plus 1 equals 0 has no solutions. Now you know that's not true. They're plus and minus I. Well, here there's going to be some complex numbers involved, and it's a little bit complicated. So for our purposes and throughout calculus, you'll be dealing with real numbers. And we would say that the only real solution here is the natural log of 3 over 2. Okay. These are exponential equations. I can mix and match things like this. You can combine factoring with, all of the log stuff we've been doing. Of course, all the old-fashioned equation solving rules like multiply both sides by blah, or all that shit is relevant. But this is the heart of it. And those basic steps I gave you are always the steps. Do whatever you got to do to isolate the exponential term. Like in that last one, we had to substitute, then factor, then set each factor equal to 0, then substitute back, then take logs of both sides, then use your properties of exponents to get things non-exponential, right? Bring your variables down, and then solve the resulting equation. This is always how it's done. There's a lot of real world problems, application problems, bank interest, half-life problems, bacterial growth, population growth, that can be modeled by exponential functions. So there's lots and lots of equations that you can come out of those. Like I tell you, the population is doubling every 5 years. I come up with an exponential function that models that population, then ask you, when are there going to be 10,000 people? That would give you an equation you have to solve. Before we look at any sort of applications, because modeling is sort of the last thing we talk about in this world, I'm going to talk about logarithm equations. We like to call them logarithmic equations. It just sounds nicer. So if an exponential equation is one where your variable is trapped in an exponent, a logarithmic equation is one where your variable is trapped inside a logarithm. And the way you solve these is like the backwards version of the way we solve exponential equations. Instead of taking logs to get variables out of exponents, we're going to exponentiate to get variables out of logs. I'll say, just recall that these two sort of crucial defining properties of logs and exponentials, the base A log of, you know, say a to the x, this is just x, and a raised to the base A log of x. This is also just x. It's really this property that we used, or the fancier version of it, the log a of x to the y or y to the x, that x can come down. We're going to do something kind of in the other direction here. There's less choice with the logarithm equations, but let me just show you, right? Showing you is the way to do it. So I'm going to start somewhat simple. Solve the ln of x is equal to 10. Now you could try to reason your way there by saying, okay, so the ln of x equals 10. That means I'm asking, like, to what power must I raise e in order to get 10 out, or something like that. Or e raised to the 10 equals something, I don't know. But what's better is to have a procedure, right? Rather than fumbling through, give yourself a procedure that works, and then develop the intuition. So what I'm going to do here is use this property. I'm going to shove both sides in the power of the base of that logarithm. Remember, we have this rule that says, x is equal to y if and only if a to the x equals a to the y. So if the natural log of x is equal to 10, then e to the ln of x is equal to e to the 10. Kind of secretly using this factor, this fact here backwards. Right? This kind of looks like this. So if I put both of those things in the exponent of the same base, they should be equal as well. Now on the left-hand side, e raised to the ln of x, well, that's like a raised to the log a of x. That's just x. So x is equal to e to the 10. This step right here has a name. You're going to call it exponentiate both sides with base. In this case, we use base e. But the new verb here, just like take logs, is your new verb for solving exponential equations. Exponentiate is the new verb for solving logarithm equations. So if you've got a variable stuck inside a logarithm, you will exponentiate using the base of that logarithm. So that's what I meant when I said you have less choice here, right? With the exponential equations, you could always use the natural log, or you could pick the base you want. Not true here, because there is, like, this one generalizes to log base a of y to the x equals y times the log base a of x, or whatever. This one does not generalize. So you have to use the same base as your logarithm when you exponentiate. That's the only catch. But this is it, you're done now. E to the 10, that's your answer. E to the 10 is quite huge. Definitely bigger than 1,000. Let's try one or two more. How's about the log log of 3x plus 5 is equal to 2. Again, I'm going to exponentiate both sides using the appropriate base. So what base will I use here?
10.
10. Yeah, because the base of this log is 10. It's not the same as raising both sides to the power, right? If I raise this to the power of e, that would be ln of x all to the power of e. But what I got was e to the power of ln x. Different things. That's why it's a different word, right? Exponentiate, not raise to the power. So careful with your verbiage, especially when you're talking about this. We're just exponentiate. So here we're going to exponentiate both sides base 10. I get 10 to the log 3x plus 5 equals 10 to the 2. Ten raised to the common log of 3x plus 5 is 3x plus 5. And 10 to the 2, that's not so bad. That's 100. I can just go ahead and write that. Now we solve. So this means that 3x is equal to 95. 95 isn't divisible by 3, so that just means x, I would write it as 95 thirds. Not so bad. The way you can complicate these is sort of similar to the way you can complicate exponential functions. I could give you multiple logs that you have to put together. So you got to isolate the log term. Let's do, do we have anything that's kind of in between there? Yeah. There's also another way these can go wrong. It's possible that you end up with domain issues. The solution you get, the number x, maybe when you try to plug it back into the original function or back into the original equation, maybe it makes this logarithm or one of the logarithms undefined. That's possible. So here, I need to first isolate the log, then exponentiate. To isolate the log, I'm going to subtract this 4, and then I'll divide over by a negative. So subtracting the 4, I get negative log of 3 minus x equals 4 minus 3, which is negative 1. Oh, sorry, 3 minus 4, which is negative 1. And then I'll divide both sides by that negative. So I get log of 3 minus x equals positive 1. And then I'll exponentiate both sides base 10. And now my left-hand side is just 3 minus x. My right-hand side, 10 to the 1, is just 10. So here x is going to be, let's see, subtract 3 from both sides, you get 7, negative 7. And you should always check. If I plug negative 7 in here, do I run into trouble? So 3 minus negative 7, that's 3 plus 7, that's 10. Oh, okay, log of 10. That's fine. The inside of the log is not negative. It's not the variable being negative that causes trouble. It's the inside of the log being negative, which, you know, can be more than just the variable. So here are your steps. First, combine all logs with variables into a single log. Isolate the log term, the log with variables. And there should only be one of them after step one. Then exponentiate both sides using the base of the log, and then solve the resulting equation. I'm going to add one more here though. So this is the step where your logarithms are going to go away. You need to check the answer. In the original equation. You see, the truth is, when you go using log rules to combine logs, you can change the domain. Specifically, when you take two logs that are like added and you bring them together into one log with multiplication inside, that can change the domain. So it's possible that the equation you get at the end gives you some extra answers, some answers that are not answers to the original problem. And that you need to watch out for. So let me show you more examples. Two more examples maybe. An example. So how about ln of x minus 1 plus ln of x plus 2 equals 1. Steps. So I need to start by, I need to get it into that form, log of some variable stuff equals constant, 1 log, all my variable stuff inside. So we need to combine these two logs. So the ln of x minus 1 plus the ln of x plus 2, that's a single ln with inside parentheses x minus 1 times parentheses x plus 2. And the right-hand side is still 1. This is using that property 1 of logs. Now, inside here, I can FOIL this out if I want, or I could leave it as it is. But if I'm going to if I'm going to solve the equation, I've isolated my log with the variables. There's no other logs or variables floating around. I need to exponentiate both sides using the base of the log. So I'll have e to these. It's really, this is challenging. E to the ln of x minus 1 times x plus 2 equals e to the 1. And on the left-hand side, e to the ln of some stuff is always just going to be that stuff. So this is x minus 1 times x plus 2 equals e to the 1, which is just e. And the result is a quadratic equation, but it's a fairly nasty quadratic equation. I'm honestly, I grabbed this example out of the book. I'm a little surprised by it. So now we need to solve this quadratic. This is x squared plus 2x minus 1x is plus x minus 2 equals e. Anybody recommend how you solve that equation? I'll give you a hint, it's not easy. It's a quadratic, it's a polynomial, so you got to pull everything to one side and factor. But e is such a weird number that there's no way in hell you're going to be able to factor this nicely. So I'll write it like this: x squared plus x minus 2 minus e equals 0. So your a here is 1, your b here is 1, and your c here is negative 2 minus e. So the only way you're going to do this is with the quadratic formula. This means x is equal to negative 1, negative b, plus or minus the square root of b squared, which is 1, minus 4 times a times c. So it's minus 4 times 1 times negative 2 minus e, all over 2a, which is just 2. This is quite intimidating, but it'll work. So that's x equals negative 1 plus or minus the square root of 1 minus, we'll do the distribution here, 1 minus, and I'll distribute the negative and the 4. So this is going to be negative 4 times negative 2 is plus 8. And then negative 4 times negative e is plus 4e all over 2. And that is negative 1 plus or minus the square root of 9 plus 4e all over 2. So you got two solutions here. One of them is x equals negative 1/2 plus the square root of 9 plus 4e over 2. And the other one is x equals negative 1/2 minus the square root of 9 plus 4e over 2. Fairly intimidating things. And I'd like to point something out. All right, exponentiate both sides. Boom, boom. Solve the resulting equation. Okay, sure. Boom, boom. That's step 4 done. Check your answer doesn't cause domain issues in the original. So this number, I don't have a good feel for how big it is. This number, I don't have a good feel for how big it is. This one I can tell is negative because I'm starting with negative 1/2 and then I'm subtracting something else, and this thing I know is positive. So this one is definitely negative. This one could be negative, could be positive. If we think about it carefully, 9, the square root of 9 is 3. So the square root of 9 plus 4e is bigger than 3, considerably bigger than 3, because 4e is actually pretty close to 12. So this is like the square root of 21 over 2. So square root of 21 is, I don't know, going to be like 4.5-ish. So this guy is, pretty close to 4. This guy is like negative 1/2 minus something 4, and then we're dividing by 2. So it's really not obvious whether either of these cause domain issues in this, but that's what we need to check. So I would, again, employ a calculator here. I want to crunch this part, the 9 plus 4e under the radical all over 2. So I'll turn this on. Second square root 9 plus 4. Then you do have an E button here. It's this guy. I take this apparatus, I hit the arrow to get out from under the square root, and then divide by 2. Yeah, about 2.22, 2.23. So this part, a little note, square root of 9 plus 40 over 2. Our estimate wasn't bad. We said the top was probably close to 4.5, right? So half of that is 2.22. We were really, really close. This is 2.23-ish. So this guy is like -1/2 plus 2.25. This guy's like -1/2 minus 2.25. I'll just go ahead and do the arithmetic. -1/2 plus 2.23. Oh, that's a 12, isn't it? Yeah. -0.5. We'll do it like that. Plus 2.23. About 1.73. And the other guy is -0.5 minus 2.23. It's about -2.73. Okay, so of these two solutions I have, do either of them cause a problem in the original equation?
The -2.73.
Good. Which equation, or which piece of the original equation, and why?
Both of them.
Very good. And it's not that it's negative. It's that when I plug it in here, that thing -1, that's negative. So any answer I get from, according to this guy, any answer I get, I need to check and make sure that it's bigger than 1. If an answer is not bigger than 1, if I try to plug an x value in here, which is not bigger than 1, the inside of this log would be negative. This guy requires that any x value I plug in is bigger than -2. So 1.73 is fine in both of these, right? This would be the ln of 0.73. This would be the ln of 3.73. Those are both fine because those are both positive numbers. But if you plug -2.73 in to this guy, you get the ln of -0.73, which is undefined. And here you get the ln of -3.73. So this, the terms for these are extraneous. This solution is no good in the original equation. The term for this is called extraneous. So the only one that we're going to hold on to is this guy. And this is a particularly difficult example, right? Because we ended up with a quadratic that involved e. Most of the logarithmic equations you will encounter in this class will not be that hard. But certainly they can get this hard and harder. Exponential equations can also get much harder, like 2 to the x equals x. Good luck. That's a truly hard equation to solve. Cannot be done analytically, in fact. So these are the basics of solving exponential and logarithm equations. You've got plenty of homework to be working on, and I am going to publish another one today. The makeup exam for anybody who missed exam 2 starts in about 3 minutes. So I need to end our meeting here and jump over to my office hours for those people. If you need anything else at all, please don't hesitate to come by office hours or send me a Canvas message. Otherwise, I will see you guys tomorrow.
I have a quick.
Tomorrow we'll be moving on to the systems material.
Just one. I'm still good for Thursday to make up my test.
Did we talk about it?
Yes.
Okay, then yes. Just come by my office hour tomorrow. I'm a little bit behind on my email, so if you wouldn't mind sending me a fresh Canvas message or email just so it's at the top of my stack and I see it and get that reminder, I would appreciate that. Oh yeah, doctor's appointment, right? Yeah, we talked. I remember. Okay, but please still send me another message. That way I see it tomorrow.
Alrighty.
Thank you. Anything else before we go, guys? All right, work hard. I love you all. Just work hard. We're almost there. I know it's difficult, but hang in there. If you get stuck on anything, don't hesitate to ask for help. Almost done, but don't give in these last few weeks because things do get harder still. Bye.